Welcome back to this lecture on rules of inference. In this third segment, we're going to use rules of inference to build proofs, to build formal proofs in propositional logic. So let's consider an argument here that's a little bit more complicated than the ones we've seen before. And the question is whether this argument is valid. Its first sentence is a conjunction. Its second sentence is a conditional. Its third sentence is another conditional. Its fourth one is yet another conditional. And its last sentence is the proposition T. So we claim this is an argument, meaning that the conclusion of the argument T is a logical consequence of the first four sentences or premises of the argument. How would you prove the validity of this argument? That's already formalized, so it's already in propositional logic. We don't have to worry about English translations here. Well, the standard algorithm so far is to build a truth table and to show that on all the rows of the truth table for which the premises are true, then the conclusion is also true. The problem with this algorithm is that in this case there are 5 different propositional variables, so the table will have 32 rows, which is pretty big. So the goal of this segment is to introduce another algorithm, or rather another approach for proving that an argument is valid. This approach is not going to be based on truth tables, and therefore it's going to produce more concise proofs or justifications for valid arguments, and it will allow us to scale to much bigger arguments that we would be able to prove with the truth table algorithm. So now we are going to write a proof, a formal proof of this argument, meaning we're going to assume that the premises S1 through S4 are true. These are given as assumptions or premises, and we're going to prove or establish the fact that T must also be true. So what is a proof? A proof is going to be a sequence of propositions. Each proposition is numbered. For example, the first one, proposition number 1, is not P and Q. Now each proposition that I state in every line of a proof must be true. Now how do we know that not P and Q here is true? We must justify that true proposition. And here it's easy to justify because we assume that the premises are true and this proposition is the same as S1. In other words, the justification for the first line in the proof, that true proposition here, is that it's a premise in the argument. So now we can go ahead and continue the proof by adding a second true proposition to the proof right under it. And this proposition is not P. Again, every proposition in a proof must be true, must be numbered, and must be justified. So how are we justified in inferring the truth of not P? Well, it says right here, we are allowed to use inference rules, namely in this case simplification. And notice simplification requires one premise, so we must indicate where the premise is. And the premise is the proposition number 1, the first line in the proof. Remember that simplification starts from a conjunction and allows you to infer that the first operand of the conjunction is also true. So not P must be true since not P and Q is true. So our proof currently contains 2 true propositions. So that's a good start. However, we're not done because neither of these propositions equals the conclusion of the argument that we are trying to prove. So we need to keep going. Now, this approach is not an algorithm because it does not tell us specifically which step to perform at every moment in time. So nobody is telling me here which should be the third proposition to add to the proof. There's a lot of art and a lot of thinking involved in writing and coming up with those proofs. For example, here, there is nothing obvious that I can see that we could infer from these 2 propositions. So I suggest that we add a new piece of information, and the only propositions we know are true are the premises. So let's say I'm going to add this premise S2 to the proof. Now, why would I choose S2? Well, the reason is because I just proved something about not P, and this is the next premise that deals with P. So maybe there will be something I can infer from this new premise. So I'm now entitled to add as a third true proposition in the proof the premise R implies P with its justification. And this turns out to be a good idea because we now realize that with this conditional being true and the negation of its conclusion being true, we can actually apply an inference rule. Do you remember which one? That's right. The modus tollens can be applied to proposition 2 and 3. So let's do that on the next line, the fourth line, and that allows us to infer not R. Now don't forget to justify every inference, every line in your proof, and the justification here is the application of the inference rule called modus tollens, or MT for short, which has two premises. Don't forget to specify those. We applied that rule to line 2 and 3 in the proof, these two. And that concludes step 4 in our proof. Now, as the next step, I've decided to introduce a new premise, or to use a new premise. Since we just proved that not R is true, and not R is the hypothesis of S3, I'm going to add S3, or not R implies S, as the next line or true proposition in our proof. Again, with its justification. Notice it's a coincidence that I'm using the premises in the order that they are listed here. In general, you're allowed to use a premise at any point in time since the premises are assumed to be true. Now, having proved that not R is true, as well as not R implies S is true, I can clearly apply the inference rule of modus ponens to propositions 4 and 5, and this is my next step in the proof. Therefore, we are now entitled to infer the proposition S by applying modus ponens to propositions 4 and 5 in our proof. So how long do we keep going? Well, we keep going until we reach the conclusion of the argument that we are trying to prove, namely T. So what can we do with S, which is the last inference we made? Well, it seems like it would be useful to combine S with the next premise we haven't used yet, which is S4. So let me add it as the next step in the proof. And finally, I can use lines 6 and 7 to apply modus ponens for a second time and infer the conclusion of the conditional, namely T. Again, I justified this inference with the name of the inference rule I used and which of the propositions in the proof I use as premise. So this is the end of the proof because we finally managed to establish that T must be true using only the premises in the argument as well as intermediate propositions that we were able to prove using inference rules. So this is the conclusion, or this is our complete proof that this argument is valid. Now that we've completed our first example, we're ready to give a complete definition of a formal proof. A formal proof is a sequence of propositions. They are true propositions because each of them is either a premise, which we assume to be true, or it's the conclusion of a rule of inference whose premises are propositions that appear higher in the proof. So why can I claim that every proposition in a proof is true? Well, if it's a premise, it's obvious, that's by assumption. But how do I know, for example, that this proposition not P here must be true? That's because I inferred it using a valid form of inference called an inference rule. And as a premise for this inference rule, I only use facts or propositions already established to be true earlier in the proof, namely this one. Notice for every line in this proof that is not a premise, I am using an inference rule together with earlier propositions in the proof, that is, propositions whose number is smaller than the current line I'm on. In other words, I'm using facts I already established to infer new facts based on inference rules which are valid forms of argument. So a formal proof is another approach for proving the validity of an argument. Again, we just proved that assuming the four premises are true, then the conclusion of the argument must also be true. So the main point that you need to get out of this lecture is what a premise and an inference rule is, and then how you can use inference rules to build proofs of arguments. The concept of a proof is very important for us. We're going to write many more proofs in this class. So make sure you master the concept of a formal proof as we demonstrated it over here. Now, the other thing you're going to have to get practice with is how to write a proof. And that is very hard. How was I able, for example, to start from here, go through a series of steps, and end up at the conclusion that I wanted? There's no algorithm to tell me in which order to perform which steps. So it takes a lot of practice, a lot of intuition maybe, and it's okay if you're not comfortable writing proofs right now, but you will have to become comfortable over the next few lectures. Let me give you a hint here of how I actually built that proof when I was preparing for the lecture. It's sometimes a good idea to go backwards from what you're trying to prove. So, for example, here I was trying to prove that T is true. So then I went backward from that proposition and asked myself, well, how could I ever infer T from the premises? Well, T only appears in this premise. And notice that's the premise I used right before I finished the proof. So I know that to get T, I can use this premise. But to apply this premise, I must have S. So then I go backward and say, how could I infer S? Well, I could infer it from this premise. But to get or to apply this conditional in S3 and infer S, I need to know not R. So how could I get not R? Well, I could see that R is part of the previous premise. So maybe I can use S2 to infer something about R. And now I'm going to go against the conditional. That's when I use the modus tollens to say, if I want to know something about R, I guess I need to know something about P. Hey, the first premise tells me something about P right here. So maybe I'm going to start with the first premise, and now I can go ahead and build my proof in the forward direction. Namely, start with the premise that tells me something about P, and then use it with the second premise to infer something about R, use it with the next premise to infer something about S, and finally use that with the last premise to infer the conclusion T. So this is just a summary of the reasoning process I went through when I was building the proof. Again, you will get more occasions to practice the writing of proofs in this class, and that's one of the most important learning outcomes of this course.